Welcome to the Fast Mode podcast series. I'm Tara Nil, and with me today is Tony Chen Carusone, Chief Technology Officer at Alphawave Semi. Founded in 2017, Alphawave Semi designs industry-leading high-speed connectivity solutions for data centers, AI, 5G wireless infrastructure, data networking, autonomous vehicles, and solid-state storage. Tony joins us as part of our exclusive editorial segment on generative AI for network management. Welcome, Tony. Great to have you on today's episode.
Yeah, it's great to be here. Thanks very much.
Okay, so let's start. As Gen AI becomes more widely adopted and its performance and accuracy continue to improve, do you foresee computing becoming a significant challenge in meeting demand?
Yeah, absolutely. I mean, if you look back over the last few decades, you have to recognize that AI has been worked on for a long time. And in fact, there was a long, what's referred to as AI winter, when interest in AI was quite low, despite progress being made on a lot of the fundamental science. And so there's really two things that marked the end of that long AI winter that spawned the recent interest and investment and growth in AI compute, and that's just the increasing availability of more and more powerful compute, which is has been largely fueled by Moore's law. So progress in chip manufacturing technology allowed more and more compute, more and more memory to be packed onto a single chip. And eventually that allowed some of the amazing algorithms that had been developed over decades to be efficiently implemented in hardware at very high speed, allow the computations to be performed with massive parallelism. um, so that's one thing. And then the other thing is the availability of more specialized computing resources. So I think specifically one of the key turning points was, around 2010, 2012, some key papers recognized that GPUs, which had until then been reserved almost exclusively for graphics processing, um, could be used to perform the computations that underlie deep learning very quickly, very efficiently, much more so than CPUs. And so this combination of more powerful compute and the use of more specialized compute, again, sparked this revolution in AI that just built on the back of all this pent up R&D on the algorithm side. Um, so now, I mean, what we see continuing on today, that progress continues to be made quickly, relying heavily on more powerful compute, more specialized computing chips, and massive parallelism. So putting dozens, hundreds, thousands, moving towards hundreds of thousands of these AI acceleration processors operating in parallel on a unified network. Um, so, in doing all this, I mean, this amazing, more advanced technology now includes, advances in transistor technology, so that we're making now gate-all-around transistors instead of these planar transistors of the past. We're using advanced packaging technology to put chips side by side, separated by less than a millimeter, and stitch them together in ways so that they can perform like one massive chips. But that amazing technology has come with a lot of expense, a lot of cost. And so in rolling out this, highly parallel, very advanced computing hardware, we've created a relatively expensive supply chain, and that's going to be a challenge. That's going to be a bottleneck going forward. Like, how do we scale this out to a massive scale within a sustainable cost profile? That's going to be one of the key challenges. And so as a result, there's been a lot of investment made to broaden the supply chain, open up the doors of innovation to more players. And I think as a result, you're seeing, new players coming out with new hardware solutions. And, Alphawave is an example of that. We work with others as well to develop new and innovative solutions for the compute and networking challenges around AI to help to keep this scaling going.
So yeah, fantastic. So you've explained about the computing side of things. So now we have data centers hosting this computing, on their platforms. So what is the implication on the connectivity bit? Because at the end of the day, all the users will be connecting to those resources, all the computing stuff that's going on. So how's the network load going to be? And how do connectivity solutions enable that?
Yeah, I mean, that's one of the key bottlenecks here is there's several bottlenecks that are popping up as we try and scale out AI processors to these really massively parallel clusters. Some key ones I don't want to understate are you delivering power, the necessary power into these racks to power up all the compute, cooling them, you're removing that heat as the power is dissipated. But key ones as well arise around connectivity. So if you're going to use massively parallel processing, obviously you've got to have them tightly networked together. And when it comes to AI, what that means is you've got these individual AI accelerator chips, and they have to access each other's memory seamlessly as if it was their own memory. And so as a result, there's these dedicated backend networks that are being created just to allow those AI accelerators to connect to each other. So this is a new connectivity challenge that's emerged and for which Alphawave and others are developing innovative solutions to try to make sure that that doesn't become more and more of a bottleneck. One of the key, as an example, one of the key ways that this is sort of a unique networking application for which new innovative solutions have to be developed. An example of that is that once these AI accelerators are configured into the network and are working together on a specific workload, the traffic in that backend network flows quite continuously. There's constant memory transactions streaming over them in a regular pattern with very high activity factor. So this is somewhat unlike traditional Ethernet networks where packets of traffic flow in bursts, and there's generally some redundancy in the network. The network's kind of over provisioned to handle peak workloads and to be resilient so that traffic can be rerouted. But on these backend networks, that's not the case. There's an emphasis on getting the data efficiently and with low latency from one place to another. So what it means is that if there's even one link that's unreliable or that's sort of flapping up and down, that can bottleneck the performance of the whole cluster. And that is very expensive hardware that would be left underutilized in that case. So as a result, there's a high emphasis on reliability and robustness on these backend networks. That's somewhat of a unique requirement. So this is just one example where new innovative connectivity solutions are essential to the continued scaling of AI. Another is just in accessing memory. These AI processors have to communicate with memory, with very high speed and low latency. So that creates another unique challenge. And then just a third connectivity challenge that I think is interesting and often overlooked, and that's key to scaling AI hardware, is the fact that virtually all the new high performance AI acceleration processors that are under development now rely on multiple chiplets stitched together within a package side by side. And so even though they're less than a millimeter apart, it's a new difficult connectivity challenge to allow those two chiplets to talk to each other with enough bandwidth that they behave effectively as one big chip. So there's sort of connectivity challenges at all different levels here that are arising and underlie all the progress we're making on generative AI.
Just wanting to know a little bit more on what you've just explained. Would that mean that data centers would now have to transition to a different type of architecture, or would it be like an incremental improvement to whatever they already have?
What you're seeing is sort of a two distinct architectures emerging. There continues to be the traditional Ethernet-based networks for what's referred to as the front-end network that connects, a bunch of compute servers together in a data center and out to the wider world that handles incoming and outgoing requests and moves data into storage and back again. So that's going to continue to be there. This is like a hierarchical network with a few tiers of switches, and again, that allows for sort of robustness and resiliency so that packets can be rerouted. But then you've got these isolated networks that are just for the AI accelerators to communicate with each other. And they're evolving on a separate path, really, because they do have these unique requirements that I alluded to earlier. What an interesting thing you're seeing, though, is that the push for scaling those AI clusters has made it so that right now we're seeing that the demands on those backend networks are outstripping those on the front end networks. For example, they're moving to the next higher data rate likely sooner than the front end networks are, which means that a lot of the R&D investment, a lot of the R&D agenda at organizations like Alphawave is focused on the connectivity challenges on those AI backend networks first. And probably what you'll see over time is the traditional front-end Ethernet networks will catch up in terms of data rate, but will leverage a lot of the same technology originally developed for the backend networks and sort of piggyback off of that. Whereas in the past, the opposite's been true.
So what you're saying is that whatever is happening in the backend networks in that scene will sooner or later be adapted and be adopted in the front end portion of in the Ethernet networks and will that also result in a surge in demand for solutions like Alphawave?
Yeah, no, absolutely. We're preparing ourselves to address a lot of these challenges. I mean, we've talked about the tremendous cost of scaling all that AI hardware. So we're developing solutions that allow for extending the reach and data rate over which we can communicate over copper cables as opposed to optical fibers, because that's a low cost way to connect racks of equipment together. So if we can extend the data rate over which we can communicate uh, over copper cables to a few meters, that allows neighboring racks to communicate with each other. And that's going to lower the cost of the end solution a lot compared to having to use optical connections everywhere. Also, another key area of focus is keeping the power consumption of all the connectivity low. This is key for the reasons we mentioned. Remember, the power delivery and cooling are other significant bottlenecks in these systems. And so if you can lower the power consumption of the connectivity, that helps alleviate those other bottlenecks that are essential. Then you've just got, as these clusters get bigger and bigger, again, you're going to hundreds and thousands of them. You're necessarily having to communicate over longer and longer distances, right? So from within a rack to hundreds of meters across a data center, you've got to maintain these low latency connections. So that's where new low cost, low latency optical connections are essential. And then I think in the extreme case, what you're seeing is some AI clusters are even being scaled beyond a single building, right? So we're trying to connect multiple warehouse-sized buildings together to form a single virtual AI data center. And so and those buildings may be 2 to 10 kilometers apart. So you need a tremendous pipe of data connectivity between those two buildings so that, again, they behave as essentially one big data center. So that's a new interesting connectivity challenge that Alphawave's quite focused on.
Okay. Amazing when we look at the complexities that come from Gen AI. On the outset, it just looks like, there are more prompt windows right now, and then you just type in and all that. And people talk a lot about data and how you manage the data and all that. But now we see the complexities in what's happening in terms of how you are connecting all those pieces together in a very robust, resilient backend network and the technologies that go into supporting that. Okay, so let's now look at the standards part that govern these environments. So how do standards like CXL and the PCIe7 improve the design of high-speed connectivity solutions for Gen AI?
Yeah, I think standards-based solutions are facing a combination of unique challenge and opportunities in being part of the scaling of AI. There's the old saying that says if you want to go fast, go alone. If you want to go far, go together. And I think now what we're trying to do with generative AI is we're trying to go fast and far, right? So what do we do? Uh, so I think what's what we need to scale out AI on a massive scale is a robust supply chain. So you need multiple players being able to contribute their technologies, and that those technologies have to interoperate with each other. And that's where standards come in, right? Standardization allows company A and company B to develop their technology independently, um, bring their own unique solutions to bear on a specific problem, and one may be ideally suited to solving, customer X's problem, and another solution may be ideally suited to solving customer Y's problem. But in the end, in order for them to be integrated, they need, some interoperability is necessary there. So that's what's the main role of standards is to codify, in particular, connectivity so that, company A solution can talk to company B solution. You can plug and play and be assured that the system will work. But on the other hand, agreeing on every detail of those, connections, the protocol, how do these links wake up and how do they go into low power states and so on, that takes time. It takes people from representatives from all these companies to come together, lots of meetings and debates and discussion, and you have to consider every corner case, and that can take years to settle on, which is not in line with the timelines, the sort of annual cadence upon which hardware upgrades are now being demanded in support of AI scaling. So I think you're going to see a combination of approaches. You may see initial solutions developed with a smaller group of players, and then standards bodies following along to dot all the I's and cross all the T's, because there is a benefit to having a broader community take a look at a problem and again consider every corner case, everything that could go wrong, and develop a more robust standards-based solution to it. But on the other hand, there absolutely I would expect that some hyperscalers will continue to roll out solutions in advance of the standards being available. They're not necessarily going to wait for the standard to be fully solidified to start rolling out technologies with few key partners.
Wow, I think you covered quite a bit on all this the interesting topics regarding Gen AI and the networks that support it, especially the backend networks that you pointed out, and and the collaboration that's needed in terms of standardization and all that. Okay, so before we end our session, I just would like to know that it's a growing space, right? And do you expect more players to come into this space, especially in what Alphawave is doing? Do you see more competition happening in the future? Or is it something where the barriers of entry are quite high given the specialization that you need to cater for such niche applications?
Well, I think that the opportunity is large enough that there's been significant investment in the last few years in this area. And so that has allowed a lot of new players to get off the ground. There's a lot of really innovative startups that have been working on semiconductor solutions specifically tailored to AI over the past few years. Alphawave's been working with a number of them. And so I think you will see those folks coming out in the next couple of years with some really innovative hardware and ramping it up to volume. And I think there's plenty of opportunity to support the investment necessary for those people to come to market. I think there's plenty of appetite for it. And because there's diverse workloads and there's no one hardware architecture that's going to be ideally suited to all of them, I think a number of them, maybe not all of them, but a number of them will find a use case that's very well suited to their technology, and yet a big enough opportunity to sustain, volume production and justify going to market and building a company around that. So, yeah, I think that the next few years are going to be exciting. That way, you're going to see that specialized hardware allow for more efficiency, and that's just going to fuel rollout of more hardware. I think there's a lot of talk and a lot of promise for optimized lightweight models that don't necessarily require as much hardware, but I think at the same time, what that's going to allow for is people to take that investment and just scale it out more rapidly to more people and more distinct applications, to roll out these specialized models to more and more specific areas to help with more tasks. So yeah, I'm very excited about the next couple of years.
Well, yep, it indeed is a very exciting space. And with that, I think we have come to the end of the session. Well, thank you, Tony, for joining us today and sharing your insights. And also the journey of going fast and also going far. That's an interesting one. I've heard that it's a popular African proverb, I think, and it's great. We talked about data center connectivity and how it's going to support generative AI and the complexities that abound. So, yeah, is there anything else you want to add?
No, it's been a great conversation. Yeah, thanks for the opportunity.
All right. Okay, then. And for everyone tuning in, thank you guys for listening. If you want to learn more, visit awavesemi.com. So I spelled it out there. And follow us for more updates and insights as we continue to uncover the latest in technology and telecommunications. See you in our next session. Bye-bye.